Welcome to this fourth video from this Lecture 3 series where we're just going over some problems from the lecture notes so that we didn't have a whole lot of time to cover in great detail in class. This is a set of notes that's focused a lot on just these basic definitions of lim sup and lim inf. And it's really important to, I think, whenever you see lim sup of sequence Sn, think of writing down this that's the definition of it. You're taking the limit as n goes to infinity of the set of numbers or symbols, because they might be positive infinity, of the sup of the set Sn, and here's the index basically for that sequence. And so we've gone over that a bit in class, but now we're going to solve some problems in section 12 with that. So I have 12.1 here. This is one where we have two sequences, and we're basically saying, look, eventually there's some point in the sequences such that Sn is less than or equal to Tn for all the points after that. And you can make that less than or equal, it doesn't matter. And we've seen problems like this. And then we're trying to show things like, well, show that the lim inf of Sn is bounded above by the lim inf of Tn, and the lim sup of Sn is bounded above by the lim sup of Tn. It's kind of similar to some other exercises we've done. I go through the proof here. It's actually not too bad, so I don't want to comment too much on it, but it basically, this is the basic thing I want to point out, is I'm letting in, because that's what I really want to establish is the index for this kind of sequence of terms. I'm letting capital N be something that's greater than n naught, because it's only after that n naught I'm doing it in the form of problems, given that you have this inequality holds. And then I'm also letting little n be greater than or equal to capital N. Because as soon as that happens, right, this relationship holds. So I say, okay, well then, the Sn terms are less than or equal to Tn. So if that's true, then the Sn is also less than or equal to the sup over all the Tn greater than or equal, where the n is greater than or equal to capital N. So this tells me that this sup is an upper bound for the set of numbers Sn that are greater than or equal to n, because this was just some arbitrary n, and I've now established an upper bound for it, for this set. Well, what does that mean? The sup of this set is the least of all upper bounds, so it has to have this relationship to this specific upper bound, okay? It has to be less than or equal to it. And so then, what do? I use exercise 9.9c, which it says basically, you have these inequalities, and if the limits exist, then the limit of this one has to be less than or equal to the limit of this one. And I'm just going to then take the limit, right? The limits exist. Take the limits as capital N goes to infinity. That's what I'm doing, okay? And then I just established this the other way in a very similar fashion for the infimum. I know Tn is greater than or equal to Sn for all these little n's greater than or equal to capital N. So again, it's like, well, that means it has to be greater than or equal to the infimum over that set. That establishes a lower bound for this set, and the infimum of this set is the greatest lower bound, right? So it has to be greater than or equal to this infimum. And again, I use exercise 9.9c. 12.3 it's not hard. What I would recommend doing, if you were solving a problem like this, is when you look at these various parts and you're asked to find the lim sups and lim infs, is just go ahead and write out what that is. Like I have to deal with Sn plus Tn here. So it's like, well, just don't guess, don't do it in your head. Just write it out right below. I'm adding these two terms down, and I'm saying I get 2, 2, 3, 1. And I look at these sequences and I just say, like, well, okay, I want to know the lim infs and the lim sups, and I just ask, like, well, what's the smallest limit that a subsequence could have, and what's the largest limit that a subsequence could have? And that would be the lim inf and the lim sup. Just answer the questions with those. 12.6, I actually have quite a bit of details in here, so you need to read them carefully. But the main thing to do in proving this result, so here you have a bounded sequence, and k is some non-negative real numbers, right? So k is greater than or equal to 0. And you're trying to prove that the lim sup of k times Sn, right, this new sequence, is k times the lim sup. So this is kind of like the result, the limit theorem result, that if limit of Sn exists, right, so if it's some real number, and then we consider the limit of the sequence that's defined by k times Sn, then it should be k times the limit. And we're just doing this right now for lim sup and if k is greater than or equal to 0. I established this claim here, and it's really important to kind of read this claim carefully, but I'm basically saying this. If k is greater than or equal to 0, S is non-empty and bounded, then the sup of k times the set S is equal to k times the sup. And you say, well, what is k times the set S? What I'm saying is k times the set S is just k times every element in the set. That's it. The proof's pretty trivial if k is 0. If k is not 0, this is what I prove the claim for. And I do this in ways we've seen. You know, I pick an arbitrary point in the set ks. That's what I'm doing here. And then I establish that k times the sup of s this is what this step's doing basically right here. And I'm just summarizing the implication of it. K times the sup of s is an upper bound, which establishes this one inequality, that the sup of ks is less than or equal to the k times the sup s. And then I just established the other inequality, you know. So I'm basically showing that a is equal to b by showing that a is less than or equal to b and a is greater than or equal to b. These are the things I'm showing. So read through the details. You have to read through them carefully, but I do it, and then once I establish the claim, the limits of these things exist, so I take the limits and use limit theorems, and that's the proof of part A. I'm not going to present the rest here. I think you can fill it in from here if you follow this argument, and it's a good idea to follow it for yourself. And then I also provide the proof of like 12.9, and well, I provide the proof of 12.9 part A. I do the scratch work for part B. And basically I make this kind of statement that part C is essentially saying if you solve this problem first, you didn't need to waste your time solving exercise 12.7, which is nice to know if you were going to solve exercise 12.7. So anyways, I'll stop the video here. There's some details here that you should read for yourself, but I just want to give a little bit of context to some of these proofs.